An approach to this problem would be to write y as a function of x. Put a little more simply, just solve for y in terms of x, or the other way around. Now this would lead to a quadratic technically this would work, I guess, or theoretically it would work. This would lead to a quadratic equation. And notice right here, though, you would have two. If y is a function of x, then you would have two x squared terms right here. So you have to combine those and involve irrational numbers. And it would be kind of a messy quadratic to solve, but it would be solvable, at least theoretically, okay? We're going to do another approach here that hinges on the fact that if you notice the last two linear terms here, this is equal to 4. These two terms right here is just equal to 4 times the given. 4 times 5x minus 3x. And so you see, this problem is kind of designed to bypass having to do this tedious approach up here. Okay, so that kind of gives us some ideas that if we can get this factor, this linear factor, 5x minus 3y, to pop out of these first three terms, we'll be down the home stretch here. So let's take a look here. Now notice that 75, which is the important, 175 has two different factorizations that are non-trivial, I guess. Or 175 is equal to 7 times 25. It's also equal to 5 times 35. Okay, equals to 5 times 35. It's also equal to 1 times 175, but it's pretty clear that those don't work if you just look at it for a moment. Okay, now right here, so I wrote down the possible factorizations, the one that involves 5x minus y, or the one that involves this guy right here. We have 5x minus y, and then we also have 7 times 25 somewhere, yeah, right here, okay. 7 times 25 right here, and then 5 times 35 right here is what I was trying to say. So it's pretty clear that the 5 times 35 should be the way to approach this, because that would lead to this common binomial factor of 5x minus y. Okay, but the question is, what do we put in front of the y's? Well, again, you have to at least try 3y. Okay, now notice the constant term in our original is 63, not a constant term, but the constant coefficient associated with y squared is 63. And so that would force a 21 to be right here. Okay. Now what we'd have to do right now is check and see if we get minus 210xy. So right here you would get 3 times 35, which is 105. And here you get 5 times 21, which is also 105. That sums up to minus 210. Okay, so this gets the job done, and that means that our original expression is just equal to this. Okay, I mean, our original expression, the thing we were trying to find the value of, the expression we're trying to find the value of, is a product of a bunch of stuff that we're familiar with. Now notice we were given that 5x minus 3y is equal to root 33 over 7. Okay, so right here we would get root, yeah, this piece right here is, sorry, this piece right here is root 33 over 7. Now right here we need to factor this also, right folks? So this would be, we can factor, what can we factor out of this? A 7. So this is 7, this piece right here would be 7 times root 33 over 7. Now I'm writing that see, it was designed to really work out this way kind of nicely, because you see this would be 7 times 5x minus 3y. But 5x minus 3y is root 33 over 7. So you see these 7s are going to cancel, but I'll just leave it there for now. Okay? And then again right here we have plus 4 times root 33. And it's possible to have just done this, but it's nice to see where everything's coming from. So I'm including some steps that we could simplify immediately for instructional purposes. All right, now what do we have? So notice these 7s cancel. These two 7s cancel. And so what we have here is 33 over 7. See, this whole piece right here just craps out into 33 over 7 because these two 7s cancel. Root 33 times root 33 is 33, and you have the 7 down here. Then right here we have plus 4 root 33 over 7. So we have a built-in common denominator, namely 7. And so our final answer here, as simplified as you can get really, would be 33 summed with 4 root 33. Quantity divided by 7. That's the answer. And again, this is from a kind of a famous class of problems where we never had to solve for x and y. We still don't know what the value of x and y is, but we know what this expression evaluates to, which is kind of fascinating to me. All right, we don't have any idea what x or y are. However, the initial conditions allowed us to solve for this expression that depended on the values of both x and y. So it's kind of neat. It's kind of a backdoor sort of approach. Now, again, for those of you who don't trust this method, go ahead and do what I said at the beginning. Solve for y in terms of x or x in terms of y. Turn it to a quadratic either in the variable x or the variable y. Use the quadratic formula. You can complete the square, whatever you want to do. Use a quadratic formula and get the answer. And it should coincide with this result right here. But I do want to stand by the fact that this approach is the most principled approach, but the way the problem was set up where we had two of the terms being a scalar multiple of the given condition, that gives us a hint there must be an easier method. Okay. All right. I think that does it, folks. Again, 33 plus 4 root 33 divided by 7 is the solution.